Hi, good morning, good afternoon, everyone. Thank you for joining the webinar series of Frontiers of Biomedical Imaging and Analysis. This webinar series are hosted by the Technical Committee of Biomedical Imaging and Image Processing, BIIP, under IEEE EMBS Society. So today we have the pleasure of having Professor Ulas Bagci to talk about trustworthy AI for imaging-based diagnosis. Sorry, Ulas, if I pronounce your last name not correct, you can correct me later. I believe you have heard of various versions of pronunciation. Okay, Dr. Bagci is the associate professor at the Northwestern University's Radiology and Biomedical Engineering Department at Chicago, and a courtesy professor at the Center of Research in Computer Vision at UCF because he was previously with the University of Central Florida. His research interests are artificial intelligence, machine learning, and their applications in biomedical and clinical imaging. Dr. Bagci has a very impressive publication record of more than 230 peer-reviewed articles, very impressive. Previously, he was a staff scientist and a lab co-manager at the NIH, National Institutes of Health, Radiology and Imaging Science Department. Center for Infectious Disease Imaging. Dr. Bagci is the PI of 2 NIH R1 grants, again, very impressive record, and serves as the steering committee member of Artificial Intelligence Resource at the NIH. Dr. Bagci also serves as area chair of MAKI, the top conference in our area, and also for several years. He is the associate editor of top-tier journals in his fields, like IEEE, TMI, Transactions on Medical Imaging, Medical Physics, Medical Image Analysis, right? For those who work in this area, you know those are really the top-tier journals in our area. He teaches machine learning, advanced deep learning methods, computer and robot vision, and medical imaging courses. He has several international and national recognitions, including Best Paper Awards and also the Best Top Reviewer Awards. Well, without further ado, let's hand it over to Professor Bagci for his fascinating talk.
Thank you very much. This very nice overview. I'm really honored to be here, giving the presentation about the recent progress in our laboratory regarding image-based diagnosis, and I'm going to highlight why really we need the trustworthiness and robustness in these algorithms. Thank you, Pinkun and Ahmed, for this kind of invitation. So let me start with the outline of the talk. So I'll directly start with the weaknesses of current deep learning systems. So every day we see deep learning is doing that, doing this in newspapers, in TVs, and everywhere. It is impressive, and it is really helping a lot of real-world application, including high-risk applications. But I want to show that actually we are not there yet, and there are many weaknesses that we need to be aware of. And I'm going to actually propose a system which is based on 3 different cores for a trustworthy AI system. I'm proposing that we really need to have at least 3 components. The first one is algorithm robustness. The other one is explainability or interpretation. And especially for image-based diagnosis, we are proposing that human-in-the-loop systems, when there is an expert in the loop for machine learning decision systems, the systems are going to be more trustable. And I will show, experiments and results from lung, prostate, pancreas, and the brain cancer imaging results, and we'll conclude with the the discussion. So maybe some of you already saw that where AI fails, and they fail very badly. There are, for example, in this case, the robot, this is the AI passport checker rejects an Asian man's application because eyes are considered closed. And in another, actually, the bias, algorithm bias, where algorithm and data bias, that the robot judge a beauty contest and don't select women with dark skin. And there are many more, like, we know the Uber and, other accidents with autonomous driving. Amazon and others, the big companies, AI recruiting tools for gender bias, Google translation errors, coming from data or algorithm, and many actually failures we can mention from AI and computer vision world. Particularly for medical imaging, I want to show this very nice example. It was actually published in 2019 Science magazine from Harvard Group. So this is a simple dermatoscopic image of a benign cyst, and the AI algorithm says that this is benign, right? It is correct. This is just a cyst, but if you put a little bit noise on it, you can consider this like several high school students and university students are taking the pictures with iPhone or mobile phone, this cyst for skin cancer, and they do projects. So rotation and different kind of the lighting or different kind of mobile phone you can consider, you will easily add some noise. And when you add this noise, the perception doesn't change for a physician. However, what changes is the AI's decision system is changing. It starts saying that this is malignant. Overall, our high-level perception doesn't change, but the AI's decision is changing. So it's a very fragile system, right? So with just a little bit noise, the same thing happens when you rotate the images as well. So rotate the image a little bit more than 30%, for example, then we notice that the benign decision is being a malignant decision with an AI system. So this is one way of actual failure. And so, we can say that commonly used deep learning algorithms are very fragile and they are not really robust. So when you look at also the papers, like every day, so many papers are coming in this field, incremental, most of them, and just trying to improve the accuracy, robustness, and, scientists develop algorithm to find, where these algorithms are going to fail, and they try to robustify. So these are good attempts. And many of the scientists are actually now aware of this. Especially this is important for high-risk applications, like in diagnosis, like in autonomous driving, and similar things. So this is also another recent paper I just want to mention. This is a really fun one from Marlene's Brugne's group in Copenhagen. So that's called adversarial heart attack. Very recently came. So authors here show that for a clean image X-ray, they put adversarial noise with the shape of heart in the middle. If you can, see here, let me show somewhere here. And then what happened is that at the end, actually, the segmentation, the state-of-the-art segmentation algorithm actually starts showing that the heart in this shape actually fakes. So this is also showing that even the state-of-the-art algorithms are not really robust and can be, manipulated. And here, their algorithms showing consistently actually segmenting the heart with the, this fake shape, and actually showing the necessity of developing a better algorithm for high-risk applications. So for today's talk, and actually also our experience in the high-risk application, especially in image-based diagnosis systems, we have actually three core components for having a trustworthy AI algorithm, AI system. Let's say the first actually is develop an algorithm which is robust. It's not easily changed to it's a decision and prediction, and it doesn't really fail easily. The second one, it is the interpretable machine learning methods, which I'm going to actually mention here. So a machine learning AI system should interpret its decision, especially for high-risk application, so that actually we can understand based on what criteria the decisions are coming. And the other one is the human, or let's say expert in the loop systems, where the basic idea is really simple. Right, humans are better than computers in high-level tasks like recognition and in reasoning. And loop, having combined two brains, one of them is the local task like deep learning, the other one is the reasoning task like human, is gonna be more trustable. So today, I'm gonna actually mostly focus on the second and third parts. And the first part, of course, I will also give some brief introduction And I'm sure that actually many of our research mostly really in the the first part, like algorithm robustness. So we try to develop better algorithms. And if you look at the papers and all those things, you will see that the algorithm A is better than B from accuracy and all other side. A new network system for the the same problems, and it comes every day. So I'm sure many of you are already aware of this. And I will very briefly explain, how we can approach this problem. It's not, of course, easy. It's an ongoing problem, but I want to mostly focus on, the second and third, and share some very interesting results from, our lab, which are, I believe, it is promising, and maybe you will also find this, the same system. Probably we can extend them into the, different system, especially for imaging-based diagnosis system. For the algorithm robustness, let me, start very briefly. So many of the, these network systems, the predictions are, compared usually based on the accuracy. So the algorithm A is better than B, network A is better than B. In vice versa, in different applications with small, the twist and fine tuning, more data, and other optimization systems, the opposite can be shown too. So the overall, actually, the one of the take-home message actually here is that not only accuracy, but we need to really choose neural network, which has, the other capabilities as well to have a better robustness system. For example, choosing a neural network which has wide enough and, deep enough, but using the less parameters, then actually you will avoid overfitting problems, right? So this is gonna be, for example, one way to increase the robustness, hence trustworthiness increasing. So capable of using less data to converge. I mean, this is the same inference, right? So the real intelligence uses less data, sometimes no data to infer something. On the other hand, the current deep learning systems are using the huge amount of data. So they are still in the artificial age, right? So we need to be using the smarter, deep learning system that utilize less data to converge. And actually, we see that such neural networks are coming. And when you actually do manipulation to your images, like I have shown this example, so it should really give consistent results. So they should be resistant to those attacks, for example, right? So we can actually increase this list, algorithm robustness from the optimization side, from the data side, from the bias side. However, we really need to start with something like the robust algorithm, so that the overall system is gonna be in the the one step the above in the robustness. Or another thing, like many of those algorithms we see in papers, that taking a good algorithm, taking a good deep learning system, and try to robustify it with adversarial attacks, or changing the the underlying connections, and pruning it using the less parameters, and the utilizing the more data variation instead of the data size, and so on. So this is like a really, I'm saying that this, in the first sense, although this is like a, the take-home message for the algorithm robustness. So we really need to develop robust algorithm when we start. And if you remember, like how AlexNet came, and now, we have much more algorithms every day is coming, and some of them actually are here compared to, the operations and their top one accuracy in the famous ImageNet experiment. And most recently, it is even more, like all with, coming with different jargon names, and it's very difficult even, to memorize their names. But this is just very recent figure showing all these different variations of the, the algorithms. So almost every day we see mostly incremental, but new machine learning algorithms are coming. So from this sense, actually, we can broadly classify the algorithms into like a CNN-based algorithms, GAN, adversary-based, algorithm. Especially nowadays, transformers are very famous. We can consider them, and also it is less famous, but it's pretty interesting that we are using a lot in our group, that the capsule-based algorithms, and this can be expanded more. However, it is fair enough to actually say the family of algorithms. So we can consider like choosing an appropriate algorithm from these classes, and then either try to do a good design or a robust design, or maybe we can robustify if there are actually weaknesses. Okay, so one example among all these family, again, like we can choose any of them. One example is that is capsule network that I'm gonna actually show how it is really robust. So, you know, compared to CNN algorithms, you know, this is called Picasso effect. So in the left-hand side, there is a face. Right-hand side, you know, the object and parts relationship are changed. The CNN will consider the right image also as a face because of its components. However, you know, object and part relationship are, you know, destroyed. Sometimes, and in many of these high-risk applications, we may really need to know the, you know, interrelationship between these objects and parts. So CapsuleNet actually is gonna, you know, to cover, you know, the such, you know, the failures, and it is gonna actually provide you the object and, you know, the parts relationship with less parameters. And, you know, one of the things in, like in CNN, this is affecting this and causing this Picasso effect is the, you know, the pooling operation. Pooling operation is, of course, necessary because you are reducing the memory burden, but you throw away a lot of information. So in Capsule, you don't really have that. And CNN actually, because of this pooling operation and a few other things, you know, CNN solely cares about the existing of an object, but their spatial relationships are not really there. So consider that you are looking for, you know, some imaging biomarker exploration, and in the body, you know, imaging base. Let's say you do that, a object and it is neighborhood, and it is also even relationship with other organs, or as a system level, you know, the approach that can be very important to, you know, define such imaging biomarker. Although CNN is gonna give you just you know, losing that information really. So it's very powerful in terms of capturing the local details, but it is really throw away such information that may be very important. So in capsule networks actually is coming from, like, you have two simple changes from CNN, and it is more difficult to, I mean, CNN is more established, that there are so many codes, libraries and everything, and capsule is going in that direction too now. The features, instead of actually just one scalar, it is represented as a vector, and this vector include the orientation informations of the objects and parts. And you know, instead of how we actually find this agreement between object and parts, we look at actually this vectors relationship with each other, and the higher level of the features are, you know, contained in these vectors, and of course, its memory is going to be more you know, the difficult, but at the same time, we will actually reduce the parameter space efficiently. This is one toy example actually showing, again, from Hinton's group, showing how objects are represented. It is like a coordinate system. Objects are represented, and since each of them are related to each other by vectors, wherever you change, you do you know, the conversion or rotation and all those things, you know, you will not really lose object information. So what happens is that it's a very simple experiment. We tried this with the failure examples that Science magazine was showing. So we did this rotation. Since the object and the part you see with the vectors are not really changing, then the decision is not going to change. But in the CNN algorithm, it was changing. Very simple. Though you can also consider that because of this rotation, probably you don't really need a lot of data augmentation, right? Because objects and parts are already captured in the variation domain already. So it requires less training data for good generalization and preserve the part-whole relationship. So briefly, capsules are actually have these benefits over the CNN algorithms. And again, like so in our actually trustworthy AI, so you need to choose any algorithm which has benefits, robustness benefits, and if not, actually you can actually robustify. In our case, I'm just trying to show, you know, the capsules has already natural, you know, the benefits that we can work, and it also fits into several of our applications. And still, actually, we develop more advanced versions of the initial capsule net. So based on this capsule net from Hinton's group, so we developed like SegCaps, which is segmentation capsules, which got the state-of-the-art segmentation results in several domains. And we have these BCaps, Bayesian capsules. We do uncertainty quantification. Again, you see, based on, you know, the SegCaps net, actually we are developing more algorithm for robust and suitable for the different application. We have XCaps we publish in MICAI. It's explainable capsules. So it does diagnosis, but it also explains the result. It is simply like a multitask learning, which I'm going to show example. We have diagnostic capsule, it does classification, deformable capsule, object detection, and we have a few other things ongoing. So we call it actually capsule soup. Like in CNN, right? You have AlexNet, ResNet, and it goes like this. So this field is also, in this case, it has less parameters, it captures object-part relationship, and then it is also, the more robust. And the first step was, create a robust algorithm. Then try to interpret, and if possible for high-risk application, include human in the loop system. And these three models are gonna give you a trustworthy AI system. So the C-CAD is nothing but actually very simple modification of UNet application, which is the one of the most famous, the segmentation algorithm. Of course, the baseline, everybody use this, and of course there are many more advanced version of this, but it is really landmark paper there. It is, you have encoder, decoder, so all the convolution and all the layers actually are, in our case, are replaced by capsules. And we initially published this in MIDL and then medical image analysis. We are showing that, for the lung segmentation algorithm, initially we show our results that we get, the similar to the UNet, maybe even better than that in terms of accuracy. In terms of parameter, more than 90% of the, the parameter space are reduced. So less overfitting, less data to generalize, and more robust. And we have other examples from other fields as well, not only medical imaging, but in C-CAPs and UNet comparison, just rotate the images. The C-CAPs is more resistant, and it is giving you a better results consistently more than UNet. And this is another example where, you just rotate it and, the UNet is failing, and many other algorithms are also failing as well, while C-CAPs is actually producing, the better results. So again, like we have VCAPs and all algorithms. So the idea is here that use a better algorithm that is more robust than others, so that your system is not gonna fail for the simple rotation, simple noise addition, or when it comes from different scanners or different patient groups. So it's mostly actually I want to show also the second part where, okay, once you have a good algorithm and you want to do image-based diagnosis, we really need some reasoning or interpretation for your system to, to give reason about why the system is picking up that number. It can be like malignant or benign, or it can be some other diagnostic decision, and it should actually explain with some ways so that actually we can trust. Patient can trust, the doctors can trust. Here I want to say that actually there are this interpretable and explainable terminology used exchangeably. However, actually we believe that even in the literature there are some ambiguity between those definitions. I use interpretable terminology for the model interpretability, which is not really reasoning. Explainability is more like how, in our case, it's going to be radiologists or pathologists, how physicians are interpreting at a high level. Still, true reasoning system is not available yet, so I'm going to put them, the mentions on the explainable side, like how physicians are interpreting these results. So interpretable ML is going to be considered like a model interpretation, which is a different thing. Okay, so many of these the problems in deep learning is 70% of the deep learning, the statistics says, is using the images, the high dimensional data. So any word problem, let's say, so you have a sensors, it can be imaging, like in our case radiology imaging. So you have the data. And most of these, deep learning algorithms is a black box model. It doesn't have, they don't really have any, the interpretation systems, right? The explainability systems. And, the features they are deciding those results are usually high dimensional, and it's very difficult to interpret what they really mean. And it just spits up a number, right? The classification results, and you expect the human, in our case, this can be patients and the physician to trust this result. So the simple thing in high-risk applications, so why should really they trust your decision? So if there is no the reasoning and supporting documents. So these explainability methods actually come in different ways. So if you really have the such steps as an ad hoc, or just in one system you have this, you are going to increase the the trustworthiness. And there are many ways to do that. And, you know, it's not a new problem. So if you go back to just, you know, the older algorithms like decision trees, regression algorithms, and even very simple classification rules, there are, you know, these linear systems are more explainable, right? It gives explanation, but the accuracy was never there because the problems are highly, you know, the complex and nonlinear. So neural networks are doing really great in accuracy, but not really explainability. The idea is actually having the neural networks like high accuracy, but move that actually the ball onto the right-hand side, which is higher explanations, are gonna be the main goal for a system which you can trust. And when I say, like, you know, this explainable algorithm, so it should really say, of course, this depends on application, but for this particular application from DARPA web page, you know, it shows if the decision is CAD for a, you know, the image, so it should really explain like why it is CAD, like it has fewer, whisker, claws, and, you know, several other features can say. The current explanation of the deep learning is like it just says CAD. The same thing in image-based diagnosis, right? A tumor is benign or malignant, or prediction of the recurrence of a tumor, right? In terms of timing. So without having any explanations. So we need to really, you know, avoid this. However, this topic is also a little bit, you know, has subjective, you know, definitions. So interpretation or explainability is really domain-specific notion. So there is not one purpose definition. So you know, the interpretability you do in image-based diagnosis, like in lung cancer or prostate cancer and autonomous driving, they are all going to be different. Physicians are going to be, you know, analyzing the results differently in prostate, in pancreas, in all those things. So this nice article is also, you know, saying that interpretable machine learning, but to whom and which application. So there is not one purpose definition for every problem. So you initially define what are the potential explainability criteria. Then based on those, actually, we can, you know, go for. And again, the first step was to, you know, create an algorithm, you know, the backbone, which is robust. Second, now create the explainability criteria to increase the robustness and attach them to your robust system. So one example, so how, you know, interpretation can be what? So this is lung nodule, you know, the lung cancer experiment with CT, low-dose CT. When the radiologists actually, this famous LIDC data set, when the radiologists actually give, I think these are also based on the ground truth there for nodules, they're malignant and benign. So they also, morphologically, they also give scores, like how those nodules look like. So this is radiographical interpretation. So what is the sphericity of a given nodules or margin, lobulation, texture? So they give some score. So this is the radiographical interpretation, and they can be attached to learning mechanism of, you know, and nodules you are defining as a malignant or benign. So at the same time, if we learn all this radiographical interpretation, and if we define the machine learning based prediction with this radiographical interpretation, it is like actually you are imitating a radiologist, and they will understand from these morphological operations how these decisions are coming. You know, in another example, like radiation therapy interpretation, again, you have CT, and, you know, so what we can actually include in this example, you know, it is really different. We look at the shape of the nodules again, this tumor, but we look at the density, the physician look at them, right? Location of the pathology, where it is. Morphology, like there is the fibrosis or other, there is a scar or other tissue information, texture, size. These are the information that physicians are looking at, right? So explaining the, you know, the decision about, you know, this radiation therapy treatment plan. And if your system has a, you know, the outcome, and then if your system has also outcome of these visual attributes, that is also going to be more trustable than just a single system without these visual attributes. Another example, now the third example with pancreatic cyst. You know, this is now the system again changed. Morphology properties are different than lung nodules. So we need to define those explainable, you know, the visual attributes, radiographical visual attributes, and then, you know, attach to our system's decision. how they are combined to, affect the decision of a cyst, if this cyst is gonna convert into pancreas cancer or not, right? And then we explain this not only with machine learning results, but also with their morphological properties, where this cyst are, like location is very important for this case, size, texture, and several others. And so far, actually, we define those visual attributes, actually, based on expert knowledge, like our radiologists and our physicians are saying that actually we are at this step, actually, we are not finding something like a biomarker which was not defined before, but this is the step.
8:45
So that's, I think there is a noise. Okay. So this is the step, actually we need to do it before going into unsupervised like imaging biomarker discovery, right? So experts are defining this, and then we go from there. Okay, so a simple explanation can be made by just under the multitask learning. And with capsule, if you use capsule, you can use actually anything here, but if you use capsule, so the good thing is that we can relate all these visual attributes to the decision very easily. So any algorithm, let's say CNN, ResNet, or in this case, it is the CAPS algorithm. So the CAPS algorithm is going to give the predicted diagnosis. And if you put the visual attribute of lung cancer, in this case, lung cancer, it can be therapy, it can be pancreas. And let's say there are n visual attributes you define from expert. You can learn all of them as a vector, and those vectors can be related to each other and with the predicted diagnosis. This is gonna give you some sort of actually causation as well, or a relationship, let's say, to be on the correct side. So interrelationship, all these visual attributes and the predicted diagnosis can be related with this one. Okay, so again, just I'm reminding here, there are 6 visual attributes that we learn from radiologists, but it can be more, it can be less. So it's a pretty flexible system. And in our, this experiment for lung cancer, this SOTA means actually state of the art. It's the terminology people use. So initially, if you use the SOTA CNNs, it gives pretty good predictive performance for the lung cancer diagnosis. While if you start with the CapsNet, it is somewhere lower, and it is expected. Right? The very small algorithm, it's not really that deep, this CapsNet, but it is more explainable. And with the addition that we have done, we took like explainable and the capsules, make it actually handling the large images. XCaps becomes very similar to the SOTA CNN, in terms of accuracy, but it is much more explainable. And the general trend actually when putting the explainability is like you really there is a trade-off, right? You really lose the accuracy if you remember this the first have shown. So this is the results from our Mikai paper, where the non-explainable method, the explainable methods actually we compare. The non-explainable methods doesn't give any, they don't really give anything about the visual attributes, so no radiographical interpretation. On the other hand, proposed, the CAPS, this explainable capsule actually is giving pretty good results, very close to the state of the art. Probably it's gonna be, better every day. We develop this algorithm, putting more layers and some fine tuning, including the visual predictions, and we know the results. This capsule vectors actually is telling us how they relate to each other. So this is one way, like the multitask learning. You learn visual attributes and you learn this and relate this. Probably the most famous visual interpretation scientists are using really the saliency-based methods. It is not true reasoning about the decisions, but it gives where the filters learns, where the machine learning learns their decision. So that's a very good thing actually. So it gives you an idea, like visually, if you are in the correct place or not. That is also related to robustness and trustworthiness, right? You want to see, let's say you are trying to find them, the pathology decision, and if your system is showing not pathology but some other organs, then and the result is true, you are not going to actually trust this, right? So this in terms of that, actually, this is a pretty nice approach with a lot of drawbacks, of course. So there are many explainable approaches for visual saliency, like forward pass, saliency map, the guided propagation, and many other things. And the idea is really to find the pixel which contribute maximally to that prediction. This is one way, it's the opposite way. You just get rid of some part of the images like a box, and you look at the probability plot. When there is this probability plot, the decision is showing very little, very big jump actually, and it means there is something. So this is like occlusion visualization. And so the drawbacks of these saliency methods, they are all actually post hoc. It's not truly reasoning, and attention mechanism visual attributes are not there. It just show where you really learn your features are coming from for the prediction, and they are actually very sensitive to the the noise and artifacts and all those things. Probably the most famous one is really the CAM and Grad-Cam, these visual saliency features. Here, for example, the input is the dog, and Grad-Cam is showing roughly where it is. And compared to the other explainable AI, these visual saliency methods that more or less they show the same thing with different caveats. The Grad-Cam flight actually more than others because of it is more robust and actually using the gradient information to localize into the the object most of the time in object places. That I'm going to show that it is not that case, but it can still be used. So how it works actually, these visual methods actually, you are let's say you have a classification problems. You learn from actually layers, those features places, and you just try to actually leverage the location and combine them to find the dominant regions. It gives you the the classification results. Many successful cases in the literature, it shows, for example, organ localization is something that Grad-Cam can do it. You see more or less actually it really shows this organ localization. This is one of the first steps before doing the delineation. It's very important actually. And this is our own papers with NIH. Actually, we collaborated where COVID-19 pathology detection. You see, it's not perfect, but it starts showing this consolidation and ground glass opacity regions. And we published this in Nature, I think, Communication, that Grad-Cam more or less actually shows, where the decision is made by deep learning. But it's not completely successful, that I should say. In mammography, like pathology localization, this can be used, right? And these are all good examples, again, but I want to also highlight some of the, the drawback of this, and still why we need to also even improve this one. So visual attributes was, the something. And again, I just want to remind that for every application, you need to just sit and with your experts and define those visual attributes. There is no one purpose defined, the rule for explainability in this sense. So in many cases, actually, these attention maps, the visual attention maps, there is not really ground truth, right? So it's really, the subjectives, and and the experts need to see it and just evaluate all of them. Categorical labels most of the time, healthy and unhealthy. For example, here is like a healthy and unhealthy is the COVID patients. And when you do classification, it is likely in Grad-Cam that it can focus on unrelated regions. So here, for example, those heat maps are showing the regions from outside lung. And, and then if, let's say, your algorithm says it's a true decision like COVID or the severity of the COVID, but this heat map is showing like the bones and outside lungs. So how you are gonna trust, right? So this is a problem. So instead of actually, using the Grad-Cam, actually, we can actually, improve this a little bit more. So the basic idea is really coming from information bottleneck idea. It's very actually old paper from 1999 from Tishby. So the idea is this: compress the information from the by the input, and take any deep learning algorithm. Okay, compress the information, so make it minimize so that on very minimal information goes to the other side of the network. But you still provide that information is still enough to make a good prediction. So you reach the X, and then you compress it, okay, in the bottleneck, compress it, and just pass little information. that little information is still enough to make good prediction. Okay, so that is the idea. So what you are going to do, you are going to minimize the information on the left hand side, right, or compressed information. On the right hand side, you are going to maximize the prediction still. So this is if you solve this problem, so what happens is that okay, minimize the initial information and maximize on the right hand side. So you are gonna actually find only the dominant region that is useful for your the prediction algorithm. So instead of like Grad-Cam or Salience algorithms where you are combining many feature sets and with weighted normalization. So it again, like this can be used in any algorithm, like also the Grad-Cam for COVID patients. Actually, we got the CT images and we used this ResNest, this Amazon, the extension of the ResNet, the architecture. And after we get X, we use this information bottleneck, the minimization system. You compress the data. Once you compress the data, you got X tilde, and then it goes to the the other part of the deep learning and the binary outcome. So here, what is happening? You have a label, and what you do actually, you can actually compress the data. The simple way in information theory is to put noise, right? This is the way you corrupt the data. So we do the same thing, and iteratively actually we solve this. Finally, it should be expected. It should show you, excuse me, at the visual saliency regions which are more robust. So again, like this is for prostate cancer, the MPR, the multiparametric MRI input, where you can use actually capsule instead of CNN. You can use capsule, the same algorithm. So the EBA is this information bottleneck we use, and then it is gonna localize where the the lesion is. Okay, so I'm gonna actually skip this. So this is the idea. I think you got all how the algorithm. So this visual explanation is since very important, and we want to see really the dominant region. It's really helping from the saliency part. Just want to show some examples how this differs between Grad-Cam and the EBA. So any algorithm, again, just prostate, it can be pancreas. Here it is COVID cases, positive class COVID cases with a variant level of severity, and negative class, there is no COVID. You put it into the deep learning, and then we want to see there is a positive or negative, and it can be also the severity estimations to use EBA to locate pathology. So this is the the algorithm, and let me show what happens. So I'm going to show that Grad-Cam is not really robust for many of the problems. In certain slices and with parameter tuning, you can start getting good results, but it's really difficult to the trust in many cases. So here you see it is outside the lung. Actually, Grad-Cam is showing where the pathology is learned, or the decision. And on the other hand, this EBA, this information bottleneck approach, actually is mask out unnecessary regions and only focus on the the dominant region. It has also some drawbacks still, but better than the Grad-Cam. So this is the data set, more than 1,000 images from the Russian data set, CT scans, and there are different severity cases for the CT, the COVID, and I'm gonna show the the experiment. Let me skip very quickly. So this is healthy image. You see the Grad-Cam is picking up some places. Even this is healthy, so it shows some pathology. So this is the first problem. Second, so there is this little GGO, but EBA is actually, this method actually is capturing that part very nicely. On the other hand, Grad-Cam is not really get anything here. And this is another cases. There is also here the little GGO, the pathology. And EBA is actually getting this more or less, while Grad-Cam is showing all over the place. Okay, so even your algorithm is true, let's say if it's CNN, but Grad-Cam is going to show everything. So then the trustworthiness is going to be less. So you need to choose an algorithm which you can really the trust. And this is another algorithm, another CT case where we have the pathologies, and Grad-Cam is also start getting it, but we know that also it was also all over the place, right? So our visual scoring task actually shows that in we asked 4 radiologists. In all of them, actually, EBA was this new compressed in, the compress-based system was much better than Grad-Cam for visual evaluation. And so here is another one. This is also in terms of localization, how good it is. In most of the, the system, again, our raters find the, the EBA much better than, the Grad-Cam, as these results actually shows. So, okay, so interpretation and explainability is just, there is no one purpose definition. I tried to show two of them. One is multitask learning, like visual attributes. You define your problem and add them into your classifiers. Okay, it can be segmentation to then still classify, like pixel based. And then I show visualization based system, like Grad-Cam is something, but we really need to improve it. And it can be anything else, right? So there is no, interpretable to whom. There is no one purpose definition. And again, like the first step, it was always start with a good algorithm, then put interpretation. And this is the last step. I want to show like how expert can be in the loop for very high risk applications. In many applications, I agree, like segmentation and many other things, that you don't really need human in the loop and you want to automate the systems. But for high risk applications, I think we need to, include the, the system and the expert in the loop, right? So how DeepMind is doing this joystick-based, these games, and the system learns from you, you in the middle, this machine learning system, like human in the loop and like reinforcement learning, right? So so like a two brains, like it learns from you and you learn from it. So the same idea we have for several years. But the difficulty was that you can use mouse and keyboard as a way to interact with computer as well. In radiology rooms, you need to actually, read those images as a radiologist in a very small time and no distraction environment. And actually, no really time. Their time is very valuable, and it is so. How we are gonna learn from them all those annotations is the very natural is that actually just observe them in their environment. So one way is the eye tracking systems. There are many eye tracking studies in the past, including ours. They were all in the laboratory conditions, but not in real radiology room settings. So in real radiology room settings, if we can do that and learn from them how they do the screening, how they, the understand of diagnosis, that can be something very valuable for our system. So first of all, they are experts. They know all those decisions. So including them in the machine learning system is going to increase the trust. The same for this autonomous driving cars, right? You are in the wheel, and if necessary, actually, you are just there. And the system is more trustable once there is somebody there, especially in conditions where there is a danger, right? Similar things can be expanded, not only machine, this image-based, the diagnosis system. So again, I'm going to give, first of all, examples from the lung cancer, but then I will expand this to, the prostate and brain. So in a simple CAD system, computer-aided diagnosis system for lung cancer diagnosis from CT, like nodules. So we know that expert may miss tumor. The amount of this percentage is around 35, especially very small nodules, they may miss. There are radiological biases there, like inattentional biases and satisfaction of search and many others. So this is possible. And on the other hand, we know that machine learning algorithms can find those tiny tumors. But many of these machine learning algorithms, these AI algorithms, produce many false positives that many of those CAD systems didn't go into the the clinical systems. It's very difficult because so many, and radiologists need to click that, no, this is not tumor, that is tumor. So this was one of the hurdles. So what we can do is actually the human expert can, on the other hand, easily find, which are false positive, and the machine learning algorithms are good at missing tumor cases. So there should be a true collaboration instead of just having the AI as a second opinion tool. So at this step, actually, eye tracking can be a nice interface. It's not really taking the time of radiologists, and unifying the power of this complementary strength of computer and the experts. So this is our initial system, like 5-6 years ago. We put the glass-based eye tracking system. Now we don't use, actually, we have just a desktop-based. Nobody need to wear anything. And there is a PEG system, which is a radiology system, and they read, and we track their gaze patterns, and we put them into the almost like real time, put it into CAD system, any deep learning system, let's say, and then we learn from those gaze. At the same time, we teach them where to look and if they miss anything. So that is the overall idea. And this should be in real radiologists, the room settings. That is very difficult. And combination of those gaze patterns into the deep learning algorithm is another difficulty. Because usually these are the visual map, you need to quantify them. Okay, so how we did it? Very simple again. So you have this gaze pattern from eye tracking devices. So we model them as a graph. So with your eye, you look at one point. We consider that point as a node. When your eye changes, you do searches, we utilize all these actually search space as a edges of the graph. So any gaze pattern you do with eye tracking is considered as a graph. And actually later, what we did actually, once you define this quantitatively, now you have numeric data, right? From the visual map, now you have numeric data. So it is a huge data because radiologists usually look at many places and it is very sensitive system. So there are huge data. What we do is actually we just do the clustering and sparsifying to reduce the data without losing the attention region. And then we put them into any deep learning system to the classification, segmentation, or detection. So again, like here, I want to mention that these systems, like where they look, is called biological attention, not the the computer attention that nowadays everybody use this terminology, right? So biological attention is where there's the perception, where they really look at it. And that area can be highlighted with your CNN system. Initially, we were also using CNN, and evolution of the CNN, like we need to robustify it. So nowadays, we really use the capsules in all this compartment. This is our new eye tracking device. We don't need to wear anything. You just put this under the desktop, this screen. And actually then it is pretty sensitive and it gives you these visual maps that we convert them into the graph. And then this graph is embedded into deep learning in almost real time. And we, utilize in a almost near time, real time actually manner. So it has a three system. Gaze analysis is how eye tracking and we convert them into the data. Visual attention is actually, we get this visual attention from after we reduce the data from eye tracking. And that visual attention is the perception is go to the deep learning. So true attention in the deep learning actually is unifying and you can do detection, segmentation, classification, whatever the problem. And not only actually one screen, actually we can use multiple screen. Like initially it was lung cancer screening. Now this is like the multiparametric MRI for prostate cancer. So we can even analyze like the screen even more. So the radiologists are free to look at different regions. I just want to show this nice example where our first radiologist for lung cancer screening, these yellow parts are where they look at it and we convert them into the nodes and the edges, and then we reduce them with our sparsification algorithm. In the third line, you see only those points are our attention regions from the radiologist where they look at it really. The second radiologist is looking actually a little bit more places, and third radiologists are looking more coverage region. This is based on their experience, but different experience doesn't really matter. We can still compress this information and put them into the deep learning. This opens another room actually for each of us that we want to actually pursue. It's like a personalized visual search, supported by deep learning. So for any different actually radiologist, this system can behave according to a radiologist. Where they look and where they don't look actually. I just want to show actually, this is the 4 regions. We can even understand that when radiologists look at the T2 mapping, T2 weighted images, and then go to the, the ADC, and sometimes look at the diffusion images as well when necessary. So we can even understand actually in which order they look at different images to make diagnosis. This is the personalized system again for one of the radiologists. They look at it actually, and these red regions are showing where radiologists didn't really look at it. And the system can understand because of this visual attention. We know where they cover it, where they didn't cover it. The system can focus on here, deep learning system, and do a refined search and find if there is anything here. So there was something here, for example, a little nodule and showing that, you didn't really cover here and there is a, the tumor here. So this is like really helping and collaborating with the radiologist. And the results were actually pretty high, like this, the sensitivity results for finding the nodules. So just a few 4 minutes and then I'm gonna actually finish. So can we use this for some other purposes? Yes. With Sloan Kettering, with our radiologists, actually, we did some experiments and recently published in Radiology AI journal. We use eye tracking for a rough segmentation. So what happens is that our radiologists open a brain images with tumor, just look at the tumor. In the background, we already have like a UNet-derived algorithm, and in our initially now it is segmentation, capsule segmentation. So you just look at it and our attention goes there, and then we do the rough segmentation. And then those rough segmentation can go into the refined segmentation to create ground truths. Like the ground truth is very expensive, because of radiologist time and all those things. So this can be done in real radiology room setting while they are doing their routine work. I think this is very important because in medical imaging, having the large scale data with labeling is a big issue. And then eye tracking can provide something. Eye tracking plus a background system running for the rough segmentation can be a really good setting. And for others, the organs and imaging modalities, actually we tested that you see those rough segmentations that can go into the refined segmentation for precise labeling. And not only actually the similar idea we apply to non-medical imaging application, where we are using mixed reality headset. A user is actually looking at the the bridges, and instead of pathology, we are looking for the crack. The same idea. So we use the same pathology detection and quantification method from medical images. We transfer this to civil engineering, and we implemented everything in the headset. And here, actually, the users, the human inspector, is just looking at one region, and automatically we find the crack and we quantify it. Exactly the same thing. And this is like how civil engineering actually is getting the inspiration from us. I want to show this movie as the last point. Like here, it is real time. So the inspector is looking at this region. You can consider this like anatomy, and there is a pathology, and immediately it segments. So this is real time. You just need to just click once into the region, and then a different view. You see from the different views, it still shows the detection area, and also the segmentations are showing. And again, like you can call it like a pathology detection and pathology quantification. Different versions, like the SPAL is here. It was crack initially, now SPAL. It works actually pretty good, and it's really inspiring. And this is also like human in the loop, right? The human inspectors in the loop. And they don't need the measures, just with the headset from any distance, they can do it. Okay, so that was the last actually the video piece that I show. So I can say actually the AI every day, actually we see lots of papers from archive, the conferences, journals. It continues to emerge in all fields, but it has a lot of drawbacks, especially in high-risk application like in medical imaging. And most algorithms are fragile, and we really need to actually robustify this. So in our laboratory, at least there are more, but at least 3 components that we are working for image-based diagnosis system. First, we need to start with the robust algorithms. So the robust algorithms are going to be more trustworthy. Here I show the family of capsules algorithms, which are using less parameters, and there is actually object and object component relationship are actually captured. So this has several benefits over CNN, and in more robust, that's why we use. And interpretability is something else, or explainability, like interchangeably. So that is going to increase the trustworthiness. And if explainability come in different ways. For every application, you have different explainability structures, like visual explanation is something, radiographical explanation is something. So you need to define it before the problem starts. But it should be, it should be in your list. And third, especially in image-based system, we know that you cannot really use this system everywhere, but especially high-risk systems, if possible, using the eye tracking system or headset, this mixed reality, the expert in the loop system also tied to trustworthiness because it increases the robustness. So, we did our experiments in lung cancer screening, radiation therapy planning, like head, neck, and lung, prostate, cancer for MP-MRI, pancreas stratification with MRI. All actually we got very favorable outcomes, and it also includes like different, like classical learning paradigms as well: classification, detection, segmentation. These are all actually included in all these applications. But the high level, so you need to have a robust algorithm. Explainability need to tie into that, and if possible, human-in-the-loop algorithms are preferable for these risky applications. These are my references, and thank you very much for listening. I'm happy to get any questions.
Thank you, Ulas, for this fantastic presentation. Now, are we going to trust more or less the AI after your talk? I think that's what what the attendees will think about. And we have some questions in the Q&A. And so, can you see the Q&A, or should I read it for you?
So let me try to open it.
You're muted right now, but
okay, sorry, I think I muted myself. So so the initial question was about the heart radiology example, where actually, what, authors put noise and artificially put an heart example, and then they what they did it actually, it's a system conversion to the learning just the heart, this fake heart system. So it's like a noise artificially created, and it shows just how algorithms are really fragile. Especially, it's not even just unit, but it's one of the best segmentation algorithm it was. The second question was, the images are raw data from the imaging machine, or is it report generated image? So they are actually images from the machine. In some of the examples, we use also reports from radiologists, like this radiographical interpretation for lung cancer, treatment planning. We use their report because we want to show these visual attributes are also written in their reports as a way of, the checking. So presentation, they ask if they get the presentation PDF. Yes, I'm gonna send to Ahmed and Pinkung. How will the advent of 3D imaging visualization change the way data will be processed, especially in the area of explainability? So that is a nice question. So the how 3D imaging visualization, so we do post-processing, right? If there is anything coming like an object information is tight, probably it is gonna be easier. So I not in radiology, but in other fields, I see that more and more object information and quantitative informations are attained. So probably it's gonna be easier to include them in the explainability, because object information is there. So in radiology examples that I give, we have images already, but those object information, we need to find it, right? Object, like you detect it, you segment it. Extracting the object is called segmentation we do. So that is definitely gonna improve. The AI diagnosis is gonna outperform human panel of experts. I mean, this is like, what I believe is, having two minds. One of them is really complementary to human. The local task is, the AI is pretty good. The other one is the human expert. Like, we are always better than, the AI, at least this kind of AI, in the high level task, like reasoning task. So we are not really there. So in some of our, experiments, so, and also, in our class, we give always the same example because we saw that. So let's say you have a cat picture under a tree. In one part you see a head, and other part you see the tail. AI is easily see that, there are two cats, one with head and the other one is with the tail. But as a human, you will understand, and there are many cases like this. So the AI is still artificial, and we have real intelligence. So I am in the other side. So another question.
So Professor Ulas, can you listen me, please?
Sure, go ahead, please.
Yeah. First of all, I would like to thanks for such kind of a great presentation and great talk. And so now I want to ask that you already had done a great work. And my question is that, so what's your future work? What you want to do in future?
Thank you. So actually we are, this is just the beginning. So we have actually different different ways of improving our work. One of them is really, we want to actually do like person-specific search system with eye tracking. So the system is like, the radiologist A sit here and our system learns how this radiologist search, and it is really adapted to this person. And of course, those other things like segmentation detections are really running in the background, but we learn. So I think one of the things that, in medical imaging is that we really need more data and variation to improve the system robustness. And if we integrate such system into the real radiology rooms, we will have tons of data, and algorithms are going to learn from different radiologists, because variation is more important than the bunch of data which has the less variation. This is one way to collect data, labels, and learn a better system. And of course, we have also the other the works are ongoing, like how we can really make reasoning, which is more difficult. We are actually following up some of this robotic system, how it is being done, and try to look at this causation system, like improving in the AI systems, interpreting one step further, because reasoning is not really there. So we want to do some biomarker discovery like that can help. So far, actually, we did everything like in supervised manner, right? The experts are telling, but the experts are also, not knowing everything, right? Because the imaging devices are limited. And so there may be some biomarkers, let's say imaging biomarkers, that is more representative of the, the disease. And we want to go into that step as well, like teaching them that there is a potential biomarker here, just you need to look. So we are moving from supervised learning to unsupervised learning in that case.
I just promoted Pallavi to be a panelist because she wants to ask a question.
Sure.
Hi, Ulas. Great talk. Really, really enjoyed it.
Thank you.
My question is around, robustness. So, the first half of your talk, you spoke about robustness and reproducibility of these approaches. And so my question is, we know that radiological scans have inherent noise in them, especially, talk about MRI. There's a lot of variability, bias correction
Yes.
inhomogeneity. So my question is, I have two questions actually. First question is, how robust are these approaches to that inherent noise, not
Yes.
adversarial noise, but inherent noise? And the second question is, then, as we sort of expand these approaches to data from different institutions,
Yes.
there are papers that suggest that, well, you can train the model on one side and test it on another side and you show beautiful results, but what happens to, as you sort of start to include additional sites? So just wanted to see, just wanted to hear your thoughts on how to account for those challenges.
Yeah, it's an excellent question. I think, Pallavi, we need to work together on this for a potential grant. So,
Would love
I look at this problem like we noticed that actually you are very right. Even this, let's say uncertainty, the whole uncertainty, like this noise and all other things can be considered like uncertainty. So for robustness, we look at the system from, I think we should really look at least two systems, two core points. One of them is this algorithm point of view, all these biases in algorithm, and the other one is data. So you ask from the data point, and I agree with you. With data, actually, there are uncertainties which are, I call them actually known unknowns, like in noise and artifacts and all those things. We expect them. And there are also unknown unknowns that we may not really know, but it is there. So there are very nice work about this uncertainty quantification. So what we do is actually we apply them to disseminate this noise and like the known unknowns and unknown unknowns. And we try to minimize at least these known unknowns, like those uncertainties that we know. And the remaining is actually, it is currently it is inherent there and we cannot really minimize, but we can present this to radiologists saying that, like I think your group and Anand's group has very nice paper as well, like these are the things that we cannot really minimize, but you should be aware of this. I think, when the data come from different scanners or different institutes, we look at the quality check, and then we disseminate these known unknowns and unknown unknowns, minimize the known unknowns, and the remaining is really the, you can quantify. And that quantification is really, from one center, it can be really high, the quality is really limited. At this step, we can just present this to the users. I hope it is clear. I can.
Yeah, no, I agree with you. It makes sense. I guess my question is when you talk about these models with that need so much parameter optimization, especially with capsule nets and such.
Yeah.
I guess my question is, what kind of variability do you see? Do you observe that when you have data coming in, that the accuracy drops, and it could perhaps be because the data there's so much variability in the data? Is that something you notice often? And I guess if you talk
my experience is with this is really, the variability is really huge, even from different patient group. Let's say the same institute, but different patient group or different time. So what we do is that we do data cleaning very well, because after data cleaning, it's really minimized, especially in MRI. I can say more of the work is really data cleaning and minimizing all those things. Then we see actually more reasonable and robust training strategies, optimization strategies. But if you don't really do cleaning, you are forcing your system to learn those unnecessary variation, the unnecessarily big variation. Then the system is like taking ages to converge. It's very difficult. So the data science part, data cleaning part is equivalently important like the algorithm development. We always clean them very well and check quality and all those things before putting them into the deep learning. Otherwise, it's a huge variation and it affects everything. And we recently saw this in this Bayesian capsule work. So the capsule was not really, it was converging, but the results were not good. So what we have done is we put the Bayesian, in the bottleneck, we put the Bayesian nature. So we look at the, how data is really coming. And then we look at the mean and variation of the data in the bottleneck of the capsules. And then one more time, we understand how important to clean the data. So currently we do really engineering way, instead of cleaning everything in one system.
Thanks, Ulas.
Thank you, Balavi.
So yeah, we have a few more questions on the chat.
Sure. So there is, let me see. The limit in terms of algorithm efficiency so what do you see as the limits in terms of algorithmic efficiency in the current set of AI system considered as current state of the art? So, so my main concern with the many of these papers and algorithms is that we really look at the accuracy, but I think we really need to compare algorithms from a true computer science, algorithm comparison, based on, in addition to accuracy and the efficiency, we need to look at actually how fragile they are, number of parameters, and in which conditions actually they work better. So like a old style, but I think it is gold style algorithm comparison. So it is like a lookup table, and it tells all the optimization settings and all those things. So just looking at accuracy or efficiency, I think it may be really misleading. We start, seeing papers and, the works like that. In one application, algorithm A is better than B, but in another application, it is vice versa. And also scientists are also forced to compare their algorithm under these very limited settings. I think we should really go beyond that limit and compare the algorithm parts in the direct way. and like more nowadays, like there are more standards, like there are two nice papers come out showing the standards of AI in medical imaging applications, like multi-center setting, you know, different patients group, different scanners, and not only accuracy, but several other computer science-based algorithm comparison, you know, the systems are offered. I think we should go into that for a full comparison. Okay, let me see, maybe. So there is one question about quantum computing, if they are going to change the diagnosis methodologies. So we have actually one work ongoing with the collaboration with the mathematician, a friend. So what happens is that it is much faster, first of all, and the parameter space is, you know, the less, which already mask out several difficulties like overfitting and this memorization and all those things. Again, like the full comparison is gonna be, you know, it is gonna take time because we just look at the accuracy and efficiency so far, and it has promising effect already. Accuracy is probably similar, but efficiency is much better.
Thank you, everyone. So I guess actually, there's still a lot of interesting questions we can discuss, but we have a limited time. We have to cut off now.
Sure.
Thank you, everyone, for attending. Especially thank you, Ulas, for your wonderful presentation.
Thank you very much. It was very, you know, good to be here.